Okay, it's running.
Still waiting for Kai, he wants to join.
Wants to join the party.
He's coming. Okay.
Still running on your FPGA board.
No, thanks. What's your impression of it? So we just up.
You want the door closed?
It doesn't matter. No. Yeah, sure. Then. Yeah, welcome to my talk. I'm very happy to be here today. I was invited by Bas for introducing Genode to you. Genode is actually two things. It's both a company that we founded and operating systems technology. And the talk will be focused on the latter meaning of Genode. But I will, nevertheless, I will also give you some background about how the development was started and why we decided to create a company to pursue this development. But this will be only a very short sentences. Then the main part of the talk will be about our operating systems architecture, which is pretty different from what we normally know from Unix or Windows or systems like that. I will try to demonstrate the architectural ideas. So basically on this laptop there is a prototype version running, so I assembled just yesterday. So I will give you some demonstrations of how this works and provide you with a brief overview of what components are already in place and what features are there and can be used right now. I will finish the talk with some showcases, some little demonstrations that should make the application areas of the framework visible. So first, some words about the company. It's a pretty young company. It's only 2 years old. We founded it after I finished my PhD thesis at the university. At the university, we spent many years in researching and developing microkernel-based operating systems specialized for high security, robustness, and real-time. And my friend and colleague Christian and me came up with a new architecture, a new fundamental idea of how an operating system should be organized, and we implemented a prototype, and we are so excited about it that we decided to move on, to get out of the university and put this technology to practice. And this was a decision to start a new company. The approach is to not involve any venture capital, but just to stand on our own foot. Be a small business at first, look how everything goes, and if everything goes well, then we grow slowly. We started with just 2 guys, so Christian and me, and now we are 6, 2 full-time employees and 2 half-time employees. And one big motivation for us is to engage in open source, because without open source, our development would not be possible. And as Kai already mentioned in his talk, the majority of code that needs to be in an operating system is already there in the form of various open source components that are available today. They only need to be arranged in a certain way that we will do. So, and of course we want to engage with the developers of these components. The plan is to release our software under the GPL license, and we do this on a regular basis in a 3-month release cycle. but also provide commercial licenses to customers who cannot comply with the GPL for certain reasons. For instance, because of their markets. The income of our company is generated through contract work. So we are doing consulting services. The money that we get through this work is used to fund the development of our products. That's the basic idea of how this works. And we are trying to get both parts of activity 50-50, and until now we succeeded at it. So basically we are a very small company putting 50% of our efforts into research, which is really rare, I think. The consulting activities are all around systems-related work, like low-level operating systems work, consulting about system security, networking protocols, things like that. And as a special focus, we do low-level windowing systems, low-level graphics programming. Here you see 4 examples. This is a custom widget set, which just shows how a nice application can be implemented with only 5,000 lines of code, including all the rendering routines. Here is a multi-level secure windowing system. This is a 3D engine that runs directly on a single DSP chip. And over here, there's a real-time windowing system. So these are projects that we did at our university, and we are continuing these projects right now. So one of the products that we are creating is the so-called Genode FPGA graphics product. It's a software-hardware co-design that turns a low-cost FPGA chip into a fully featured GUI solution, so that you can attach this monitor and some input devices and have a windowed graphical user interfaces with a single chip. We provide both the IP cores, the hardware IP cores for connecting the display, DVI or VGA, and also the complete software stack. So there's no operating systems needed underneath. The software is running directly on the chip. But that's not the focus of the talk. The focus is the Genode operating system. So why do we need another operating system? And is it feasible for a small company of just 4 guys or 6 guys to do such a project? So I will first give you an overview about the current state of affairs. Right now, most of the commodity operating systems still look like this. So there's a big program called the kernel that is running in a privileged mode of the processor, so it has access to all resources, all physical memory, all devices. So it can do everything. And this program is huge. It contains typically more than 1 million lines of code and contains all those functionalities like device drivers, memory management, sometimes even graphical user interface elements, file systems, and networking stack and all these stuff. This is all put into one single program. And there are 2 problems about this. First, the chances that there is a problem in this code, they are pretty high. So statistically, each 1,000 lines of code contains 1 bug. And if you have a kernel with 1 million lines of code, there are somewhere looking around thousands of bugs. So the chances that this is prone to attacks, they are pretty high. And the second problem is that once an attack is placed on such a kernel, the whole kernel can be defected. So it's really, if there is a bug in the networking code, then the whole kernel can be compromised. The problem here, which illustrates a bit like a reliability issue, but the issue goes further. It's about zero-day exploits. So in zero-day exploits, such bugs are discovered by some party, but they are not published, but they are exploited by some criminal activities, for instance, botnets. Right now we have botnets that contain more than 1 million computers in a single botnet of infected Windows PCs. And the owners of these machines do not know that they are part of a botnet, but the botmaster can issue any kind of attack at any time. So those computers are compromised without the owners of these computers knowing about it. And the only way to fix this problem is to reduce the complexity, to reduce the attack surface, to get rid of those millions of lines of code, to make the attack surface smaller. And the idea is to use a microkernel approach. In a microkernel, the kernel is not a million lines of code, but only 10,000 lines of code, like 2 orders of magnitude slower. And the kernel does only 3 functions. The first is to establish protection domains on the system in the form of address spaces. That's illustrated by the wars over here. The second function is to provide a form of execution, to provide threading, so that programs can be executed. And the third function is to let those components cooperate in a way, to send messages or to establish shared memory connections, but in a very controlled way, complying to a policy, to a security policy. So, and if something breaks in there, of course, the network code is broken, then the network doesn't work anymore, but the other components of the system are still running and could maybe issue a restart of the networking subsystem. So, okay, the idea of microkernels is really not ours, and it's already quite old. The question that is not really solved until now is how to organize those user-level components. So just putting them on a whiteboard and saying that they are isolated is fine, but somehow they must be bootstrapped, and someone needs to define which component can talk with which other component, and someone needs to define which resources can be consumed by which component. And all these questions are really hard to solve, and currently no general purpose operating system implements a microkernel, the microkernel idea with a general purpose workloads. So our goal is to remove those, to get rid of this big attack surface. The important term right now is there is a called trusted computing base. The trusted computing base is the amount of code that needs to be trusted for a certain operation. For example, if you sign an email with Thunderbird on Linux, you have to trust the code that runs in the kernel. Okay, there's 1 million lines of code or more. You have to trust all the root processes that are started that can do everything. They can compromise the whole kernel as well by just mapping a def mem, for instance. You have to trust not only all these root daemons, you also have to trust all the user applications that are running on your account, because each application can just p-trace the Enigma plugin of Thunderbird. So if you are running KDE or GNOME, you have additionally millions of lines of code involved, and your private key or your passphrase that you enter when asked for a password is actually exposed to millions of lines of code. So, and this amount of code that must be trusted is not a kind of systems parameter that is specific for the operating system, but it's different for each application. And our goal is to minimize this trusted computing base for each application individually. Classically, we see this kind of contradictions. This was already mentioned today during some talks. For instance, the observation is that security contradicts somehow with ease of use. And this contradiction is supported by a lot of observations. For example, SE Linux has not really catched on community Linux distributions because it's hard to configure. Another observation is that resource utilization and resource accountability are somehow contradicting. I'll give you an example. On a normal kernel, if an application uses networking, the kernel needs to allocate memory for the incoming network packets. So there are memory allocations needed on behalf of the application. But if one application really puts pressure on the networking, a lot of such buffers must be allocated and degrade the performance of other processes of the same system. So there is user resource utilization, tries to pretend the limitations of the resources. Another example is memory, which is transparently swapped to disk. But on the other hand, these physical resources are not accounted to the actual processes causing these effects. And another contradiction is scalability versus complexity. So, like, if I want to have a really secure system, I try to strip it down to a minimal set of code, but then I lose a lot of scalability. And the current products in the market of isolation kernels, they are pretty rigid about it. They do not allow dynamic loading of processes. You specify which partitions you will have on your system at compile time, at build time, and load fixed amount of code in these partitions and run fixed amount of threads with this predefined stacks. But this is really simplistic and it's really static. It doesn't scale. So, and our mission is to solve these conflicts. So we think that these conflicts are there are solutions for these conflicts. And the basic idea or the DNA of our system is a tree-like structure. The core is the root of the tree. It abstracts away the basic hardware, like the CPU and memory, and has no real functionality except for starting the first process in the system, which is in it. But in contrast to Unix, this creation of this init process happens like creating a new virtual environment, which is then created. It's initially empty, and core can then decide to put certain things in this virtual environment. For instance, load some code in there, or make some communication endpoints visible in there, or to put a thread in there and start executing code. But the virtual environment of this process is completely in control of core, and it's also paid for by core. So all the resources needed to create a subsystem are paid by the parent. And now the twist is that this interface between core and init works recursively. So the interface between init and the GUI is exactly the same. So you can imagine some kind of world where you can install virtual worlds, and you can really model how this virtual environment looks like as you wish. And within this virtual world, you can already, again, create a virtual world. And so you have a hierarchy of processes running. And on each level, you have the full control over your children. And the protocol between the parent and the child consists of two operations. One operation is that the child can announce to the parent that it is capable of performing a kind of service. Here in this example, this GUI process announces to the init process, I am able to serve the graphical user interface. The GUI service can do that through the only connection or communication connection which is available to the parent. So it has no idea what's going on in the system, except that there is a parent. So there's nothing else is visible. And the second operation of the interface is the use of such a service. It's a session operation. In this example, the user application asks its parent for a new GUI session, supplying some construction arguments as kind of hints what kind of session the user application expects. And the parent receives this session request and can now decide what to do. It can decide to just drop the request because it might decide that the child is not allowed to create such a session. But it also may decide to change some of these arguments, so to transform the policies that is attached to this session. And in this case, or it can also decide to implement the service itself and return a session capability to the child to a service implemented locally. Or it can decide to forward this request to its own parent, which is the case over here. And the parent in turn can also modify the session construction arguments, impose policy which is much stronger than the policy over there, and then finally open the session at the GUI server, and in return direct communication channel is established between the user application and the GUI. And so this is the kind of arbitration of how services are connected to clients in the system. But there's another important aspect to it, because a user application is able to attach physical resources to sessions. So each application has a certain quantum of memory, a memory quota, and a user application may ask the parent, when I create a GUI session, I want to spend 1 megabyte of my own quota to the server to implement the session. In this way, the server can operate on behalf of the client, but with the resources of the client. And this removes all kind of denial of service problems from the system. So in contrast, if you look at the current state of affairs if you have the X window system, any client can create any amount of windows, and these windows are paid for not by the client but by the X server. And at one time, the X server will just crash. So it's just 10 lines of code to crash the X server through a denial of source attack. And these attacks don't work in this kind of system. So the root of the process tree, that's a very important design decision what to put in there, because if you put too many stuff in there, it becomes a monolithic kernel. But we managed to get the number of functionalities pretty low. I won't go into details right now. I will just go over to the demonstration, I think. The trading of usable resources I already explained. That's another interesting or property, the way of how permissions or how security is implemented in the system. This is based on capabilities, which is a very natural way to manage rights or the idea is that at a starting time of a process, the process has no capabilities at all. It cannot do anything. It has no right. But then the parent can decide to give a certain right, for instance, a communication channel to the process, and can make this communication channel visible to the process. And once the process has this communication right, it can invoke this right, so use this capability. For instance, accessify or communicate with another party. But it can also delegate this right to another process, for example, to its children. And so you have a very simple way to keep subsystems separate, but this is just don't tell them about each other. So they are separate, they don't know each other, they cannot see each other, and so they cannot communicate. So it's very simple. Yeah.
How do you forestall leaking capabilities?
Leaking capabilities?
Yeah. If I give a capability to the Windows server to do something on my behalf, how do you enforce that the Windows server doesn't store that away or leak it to one of its other clients?
So that's a good question. So there are certain servers that are multi-level. We say that it means that they are used by multiple clients that are potentially dangerous. And these servers they are typically used to multiplex physical resources. Like the GUI server is a good example. And these must be trusted, but they can be built in a very small or very confined, or what to say, in very simple ways. So I will give the demonstration for the GUI server, and the other rule is never hand out critical capabilities to servers that do not trust. So better let the server provide you with a capability if the server is not trusted. So it's really a part of the relationships between the processes. And if you look at classical operating systems such as Linux, you implicitly trust a lot of things. Like if you open a connection to the X server, you trust the X server, and not only the X server but our other X applications. So, but you still do it because you want to need the service. So, but here there are actually several options how to do with it.
Yeah, I mean, it sounds 25 years ago. I worked on the Amoeba operating system.
Oh yeah, cool.
And so we'll take this offline afterwards.
Yeah, great. So I will give you a short demonstration of how this works. So right now you see Genode running on this laptop, and
so those slides were running on the Genode as well.
Yes.
Okay.
So it's a custom program that I just hacked together. Right. So here's a small program. It's called Launchpad, and this is running on. I will give you a kind of image of how this looks like. So here, you have the kernel underneath. Right now we are using the OKL4 microkernel, but I will come to that later. On this kernel, there's this core component, and this core component has started the init process. The init process in turn started some device drivers, for example, the frame buffer driver, the input driver, and the timer, and stuff like that. So some basic services. And this nitpicker GUI service. So this is running here. And the tutorial browser that we see here, or in this case it's this Launchpad, it's started by init directly. So we have this tree already in place. And this Launchpad can in turn create another instance of itself, for example, by just clicking here, and here you see another instance. I can switch the GUI to a kind of X-ray mode that exposes all the identities of the different screen areas by pressing a special key. And here you can really see what's going on. So here, this is the launchpad, and this is the child of the launchpad. Here you see launchpad, launchpad. Or here, launchpad, scout. So this is really the relationship between those processes. And here you could also see that when I start an application, you can say how much quota I want to donate to this application. And this is my current quota. If I start it, you will see that my current quota will get lower. And I can later remove those applications and can regain those resources. So that's what you normally expect from a general purpose operating system. But here it's now working on this tree-like structure. One special thing about this Launchpad is that it implements a special policy of how session requests are dispatched. The policy is very simple. It's if a session request comes in from a child and the service is implemented by one of the other children, we resolve the session requests by going to the respective child. But if there is no such child available, we go to the parent. So that means we can virtualize all the services that are beyond the Launchpad instance. And in particular, we can virtualize the services implemented by core. So normally, for example, we have a log service implemented in core that we use to print debug information. And this is a certain interface. And we can start another program called nitlog. This is a program that's very simple. It implements the same interface. It's exactly the same interface as used by core. And now it's announced the service to Launchpad. And when we start another application now, the service request is not connected to core, but it's connected to this instance, and you will see that the debug messages come up in this window. So we can route those session requests dynamically to different services. So it's very flexible what can be done using those mechanisms. And we can go even further. For example, we can use the nitpicker GUI server to create a new window containing another instance of a virtual frame buffer. And this program uses nitpicker, the GUI, but announces the input interface and the frame buffer interface, which is normally used by nitpicker. So now that we have started this program, we can start another instance of nitpicker. So that's the same binary that we already see running over here. And if I start this instance, it now gets connected to this virtual frame buffer. And now this instance of nitpicker announces its service nitpicker again, and now we can start another application. For example, this application. And since now nitpicker is known as a child, this application goes to here. So we can virtualize all services and can redirect service requests in an arbitrary base. And so these are exactly the same applications, but just under another policy. So we can really make use of the recursive design of the architecture. So I will remove these guys. So I will give you some other demos shortly. So the next important thing is that Genode is not a particular operating system. Normally, operating systems are developed starting with the kernel, doing a certain kernel for a certain platform, and then starting to build a userland. And this takes a lot of time. And yes, and there are several developments spread throughout the world which went this way. For example, the OKR4 kernel developed by OK Labs, they have a kernel, they have a userland. And the TU Dresden development of the Fiasco microkernel has a kernel and then created a userland. And the same for the Cosio microkernel, a development from England, which is also a kernel and then a userland implemented for the kernel. The problem with this is that they are pretty separate ecosystems in itself. And the functionality of these userlands are mostly pretty limited. So for this reason, we designed Genode in a way that it makes it possible to run on different kernels. So you can choose one of these 6 kernels as base platform for the complete operating system, and select one of the kernels that fit best your application at hand. For example, if you need real time, then certainly Fiasco, OKR4, or Pistachio are good choices. But if you want to develop things, Linux is perfect. So we can use GDB and all Linux debugging tools to develop student applications on Linux. So it really depends on the current use case. You select the kernel that fits best and run the same software. So this highlights the toolkit kind of aspect of the framework. So it's not an operating system, it's an operating system framework. A question often asked about creating a new operating system, and also talked about by Kyle today, is how to use existing software. We don't want to write everything from scratch. And the first obvious thing to do is to support existing APIs. And we have done so. We have ported FreeBSD's libc to make a kind of POSIX-like environment. We have also ported popular libraries like libstl. With the last release, we also added OpenGL through the Mesa libraries. And we also ported Qt to Genode. So you can use unmodified Qt for applications on Genode. And these are executed directly on a microkernel. And these APIs, they spawn further possibilities. For example, based on these infrastructure, further libraries can be ported like libpng or libz, libjpeg, and the Python interpreter, stuff like that. The second approach that we employ is to create runtime environments for running existing code. And the most interesting thing is our Linux device driver environment, which implements part of the Linux driver kernel that is used by Linux drivers. So we take out Linux drivers out of the Linux kernel and put them in another environment which looks exactly the same as the original Linux kernel from the perspective of the driver. But in reality, it leaves out a lot of typical Linux functionality. The process model is not there, the memory management is not there, there are no PIDs or there is no TCP/IP stack. It's a very simple glue layer, just emulating the parts of Linux that are needed by the device drivers. And by using this approach, we managed to port over large subsystems of Linux to Genode. For example, we ported USB, thanks to Dirk's we ported TCP/IP in the past, and device drivers for sound and networking. So this is really a useful approach to run a lot of device drivers on Genode. And the third approach is to use virtualization, of course. If you want to reuse existing applications in their normal environment, we can use a para-virtualized Linux based on the OKF4 kernel, or based on running on the OKF4 kernel. And this solution allows us to reuse unmodified binary compatible Linux applications as well. And yeah, I will demonstrate it in a minute. And so such virtual environments are integrated in a Genode tree in a very natural way. So they are just normal process nodes. Here is a Linux kernel running as a process node, which can be started, created at runtime, and removed. Here is a Linux device driver running in a Linux device driver environment. And here is just the cute logo of BSD because I like it. But in principle, we could also do the same for BSD or other operating systems. So now I come back to the fundamental goal that we approached, which is minimizing the trusted computing base per application. And here this image illustrates that idea. Previously, I spoke of millions of lines of code that you have to trust when signing an email. So now things get different. Let's say this is an email application over here. So the email application, of course, has to trust its parent. And this parent has to trust its parent and again and again. So the chain of parents must be trusted, of course, because there's really an ownership relationship between those parties. And then there are, of course, services that are used by these programs which must be trusted as well. But this path through the system is orders of magnitude simpler in complexity than a complete monolithic kernel. And coming to the example of a cryptographic problem, the cryptographic function for signing an email could be implemented at a very root of nearby the root of the process tree, because the crypto function does only do some arithmetic work. It doesn't need to access any devices. It needs a simple user interface for asking for passphrase, and that's all. So crypto program can be implemented with a trusted computing base of, let's say, 20,000 lines of code. And what we can do with such a component is to have a legacy or an existing mail program the user can assemble the email in the mail program, and for signing the email is handed over to this component, to this crypto component. The crypto component has locally stored the key of the user and requests a passphrase from the user directly using the GUI, and encrypts the email or signs the email and hands it back to the Thunderbird instance, which can then deliver the email. So and now you have taken Thunderbird out of the critical path of signing an email, and you don't have millions of lines of code in a trusted computing base for your crypto key, but only 20,000 lines. So it's orders of magnitude less. Speaking of lines of code, that's the current state of the project. The core component is implemented in less than 7,000 lines of code. That's for the OKR4 version. For the other kernels, it's slightly different. When adding the init process, it gets about 1,500 lines bigger. So it's 1,500 lines, that's not really much. The reason for this slight degree increase is that init reuses a lot of program logic that is also used in core. So it's very modular, the code, and we can take a lot of use of this code in the init process as well. And this leads to overall only 15,000 lines of code for the basic graphical demo scenario, including the GUI. So you can create GUI applications with a trusted computing base as low as this one, plus the kernel. If you go a bit further and if you add this application over here, this fancy Launchpad application, or this tutorial browser with these graphical effects, like if I scroll, you see this kind of magnifying effect over here. So this is quite some fancy stuff in there. You're still just at 20,000 lines of code. So this shows that if the system, even for a kind of visually appealing application, not a huge trusted computing base is needed. And to get some relation, by just enabling the support for the PNG file format into the browser application, so just for the supporting PNG image, this nearly doubles the trusted computing base. So that's quite funny, I think. And to get the same, another perspective, if we just implement this Launchpad application, not by using our custom widget set, but by using Qt. So here we have an instance that is functionally the same. So it does the same thing. But by using the Qt framework, we get a trusted computing base of more than 500,000 lines of code. So that's the perspective. So now there are some technical stuff that is the current state of the implementation. So there are lots of drivers. Recently we ported the 3D graphics infrastructure of Linux to Genode, so we can use Gaio 3D hardware accelerated on Intel GMA platforms. We have audio drivers working, networking. Recently we have added wireless networking as well. So there's constant work getting new drivers working on Genode. There are several protocol stacks that we implemented or that we support. For example, for TCP IP, we use Lightweight IP, and there's a device driver development API that we use as a basic building block for those device driver environments. So now, two other aspects are this security aspect that I already mentioned before. So it's based on capabilities, and the configuration concept of Genode is very flexible about which client can use which service, and there's a uniform configuration concept based on XML to set up the system. And this configuration concept enables us to implement mandatory access control rules into the system in a very straightforward way. For some applications, real-time is important. For example, if you want to do a multimedia applications and want the sound drivers and sound mixer running at a higher priority, you can do that on some kernels like OKR4 and Pistachio. So you can subordinate whole subsystems to a lower priority band and can do this recursively as well. So that's, I think, pretty unique, because on Linux, for example, if you're a normal user application, you cannot deal with priorities. It's not possible. You can only do that as root. With Genode, every application can use real-time priorities. So to finish the talk, I will give you two examples. I hope they run well, because I stitched them together just 2 days ago, and they are still somehow shaky. The first thing is to implement a secure graphical user interface using the nitpicker GUI. So the nitpicker GUI is just multiplexing the frame buffer in a kind of clever way. It's implemented with only less than 2,000 lines of code and can deal with windowed user interfaces. In a scenario, it will run this native application, for example, this tutorial browser or this Launchpad application or slides application you see here. And alongside, we will see a virtual frame buffer presenting the kernel output of a Linux booted right on Genode. When Linux is finished booting, it will start the X Window system, and the X Window system will again talk to nitpicker for presenting windows into individual screen areas. So I will just start it right now. If everything goes well. Sometimes I need to. I know. Sometimes it needs some attempts. So as I say, this demo is still a bit shaky. I need to get some more maybe. It's eventually it works. So now we have this window coming up. This console is not needed anymore. So there's in the background we have an X server running, and as soon as I switch to this window, you will see that the background will change. So we have the X element background. So we can set X set root whatever gray. So that's really the normal X server running, and we can use the nitpicker GUI server to identify which part of the screen belongs to which application. So here you see that all Linux stuff is in this magenta color, but the Launchpad is in gray. So you can really identify which applications you are working with. And that's also important because if Linux presents you with a Trojan horse of a password application, you can just press a key and see, oh, that's coming from Linux, it's not my native Genode application. Another security feature is that you can prevent spyware from observing the user actions. For example, I will start some spyware that comes with each Linux distribution, the XIS program, pretty familiar. It just observes the user. I switch mode. It just observes what the mouse is doing. But this is really scary. I have not set up any special privilege. Each program can do that on Linux or on X. And the same is for user input. Each program can just sample the user input. Now imagine all those programs running in your KDE session or in your GNOME session. So the opportunity for an attack is huge. So, but with Genode, if I type in a password in a special password program, and I move the mouse over here, you see the XIs cannot see anything. They cannot receive any keystrokes that I enter there. But as soon as I go over to Linux, then you will see it will resume looking at us. The second thing is an attacker might want to take screen grabs of your screen to send them over to some kind of criminal party, and by just doing something like xvd, sampling the root window and writing it into a file, it's a simple state, and by presenting the screenshot, xwd, you will see then that an attacker will only see the part of Linux, but not the other applications. So if this Linux gets infected, the damage is limited. So just to see that Linux is really a program that can be started and restarted, and the time it takes to do so, here's another Linux, and there's another one. So it's really like starting a program. So and you can go even a step further. Another kind of fancy use case. It's doing a special web browser plugin scenario. So we will start a web browser based on Qt, and it contains a TCP/IP stack. So it gets a unique IP address. So the web browser looks like a dedicated machine, and if you start multiple web browsers, each web browser will get another IP. So you have a very strict separation of those. But now it's possible to load a web page, so go to a server and request a web page. This web page can contain a plugin, which is actually a Genode program. So it's loaded to Genode, to the web browser, the web browser installs a program by using a loader service, this one. And the loader is then depacking the programs, verifying a signature, for example. This is not implemented in demo, but it should be the case. And start the program as a separate process. But this process is not visible to the web browser directly. So it's completely isolated from the web browser. So the plugin can be an arbitrary Genode process, and it's not visible to the browser. So it cannot crash the browser, because it's completely in a different part of the tree, and the browser cannot influence the plugin. So if I type in something to the plugin, only the plugin will receive the keystrokes, not the browser. And I will just demonstrate that in that idea. So by starting this web browser. So this shows the default of Qt in action. So the web browser is still behaving a bit slow, because in the background a lot of debug messages are printed. So it's really a kind of alpha software right now, but it's fully functional. You can see that it works like expected. It's an unmodified Aurora browser. And I can just enter another magic URL over here. So since I don't have any networking, I have sourced the websites locally. So starting, for example, a Qt application as browser plugin. So this is a Qt application running natively on Genode. And you can see that it's separated from the web browser by pressing the special X-ray key. And now you see that the part of the screen used by the plugin is another domain. It has nothing to do with the web browser. So you can really implement trusted applications as web browser plugins and identify them as a user. This is useful. For example, imagine a banking application. Right now, banking applications are implemented as web applications. So the web browser of the computer user is ultimately trusted with regard to all the input data that we enter into the web application. So exposing the key to millions of lines of code. But now it's become possible that we just get a native Genode application from the banking website, having it presented seamlessly in the browser window. But in reality, it's running directly on Genode. So it's taking the web browser completely out of the critical path. So we remove millions of lines of code from the trusted computing base of the banking application. And this has two good points. The first is, of course, the lower trusted computing base, and the second is that the bank can update the application at any time, because it just gets seamlessly installed as soon as the user visits the website. And when the user leaves the website, the plugin is just destroyed. And now, of course, a lot of interesting combinations become possible, because, yeah, right, we can just run Linux as a subsystem on Genode. So we can, of course, run Linux from, well, I will start with VisiBooks. Also type here. Okay. So we can start Linux in the browser. So, and we have already implemented a kind of service that provides a block device interface to Linux and uses an HTTP connection as backend. So we can stream block devices directly from the web server. And so even a huge Linux instance can be started immediately when you visit the web page, and it loads the blocks on demand from the web server. So it's pretty amazing stuff that you can do. And yeah, you want to reboot Linux? Yeah, okay. You just press the reload button of the browser.
Yeah.
So, and of course, it's a bit shaky. I will try it anyway. There is also the possibility to run more complex stuff like Tiny Core Linux, and you will see that it will start a next session, and I can start a shell over here. So it's seamless. So you can really use complete Linux distributions with this approach. So this just should outline some of the spectrum that is possible with the Genode by just using these components that are available. There's much more to see. So, for example, the 3D support that we just added, the sound support. So there are lots of things to play around. And right now we are focusing our work on those roadmap items. So to get more and more classical Unix software running on Genode, we want to add a kind of Linux emulation environment so that we can use GCC and VI and stuff like that on Genode directly without having to start Linux. Then there's work in progress to port over Genode to another platform. In this case, it's a microblaze software CPU used in FPGAs. So we can then use Genode directly on system-on-chip based platforms, so FPGA-based platforms. Then there's work in progress to design a storage concept that is really exploiting this hierarchy that we have. So this recursive system structure, how can we access files through the system structure with this virtualization property. So that's pretty challenging, and we are currently thinking about this storage problem. Another construction side is to support full virtualization through the Nova microhypervisor. So on modern PCs, you would be able to run unmodified operating systems instead of the paravirtualized Linux kernel. And combined with IO-MMU support, this would also enable us to use unmodified device drivers embedded in such operating systems. So this would make the use of existing drivers even more easy than today. So that's the talk. Thanks for attention.
How can I insert an accessibility layer?
An accessibility layer?
Yeah.
So there's the first idea is to have a kind of intercepting service that is already in place. Mm-hmm. For example, in this hierarchy, you can transparently place a monitoring component between two components. So, and if you have a component, for example, a console, a text console, which is normally displayed in a window, mm-hmm. This console interface can be transparently provided by another component, which is, for example, driving your Braille display, and without any application to be changed. So that's one idea too.
So you could compile with it BRLT2I, for instance.
So I'm not so familiar with the topic.
That's the native Linux library for Braille displays. So,
so that might be. So we should look into it maybe. So
and for the graphical interface, you use Genode. You did say? Or?
No, that's so there are several things. So they have a very simple system that just multiplexes the frame buffer into different screen regions and labels them, so that each screen region can be identified, or the user can tell them apart which application owns which screen region.
So I can use API calls.
And then you can use API calls for creating these regions. And on top of that basic mechanisms, there are different widget sets. For example, this custom-made widget set that we use for the Launchpad, but there's also the Qt framework that we ported. So it's possible to use different GUI implementations based on this.
Qt framework is not accessible at the moment, but okay.
Which framework?
You mentioned Qt?
Yeah, it's available. Yes.
Yeah, it's available, but the engine is inaccessible.
Okay. So yeah, GNOME is better in this regard.
Yes.
Yeah.
And a little KDE.
So the Qt framework was a showcase for us to really prove that this recursive structure really scales towards complex applications. And I think Qt applications are extremely complex, so they are exceeding all other toolkits that are available. And this just shows that Genode is still not breaking under this heavy weight. So that's, from us, it's more a technical challenge. It was motivated by the technical challenge, but it should be possible to support other toolkits as well, in principle. Okay. I think you were Phil.
Yeah, because that follows on to the previous question, mm-hmm. and actually to my previous question as well. I mean, if your slide 25 or 26, you had the web of trust, or the network of trust.
This one?
Yeah. Okay. Yeah. But so now, at one of those levels, I insert my accessibility module.
Mm-hmm.
Doesn't this mean that, so that means that one of my ancestors delegates some work that you know, I'm the top level program.
Mhm.
I expect to run in a certain environment, and I think that this is my trust graph.
Yeah.
But one of the layers of my parents has delegated stuff to the accessibility layer.
Yes.
So without me knowing, I'm now also trusting that accessibility
Yeah,
layer.
implicitly, that's right. You trust it.
And if I because if I sort of extend this and I look at your web browser example, then if the web browser has the ability to save downloaded files, it
Mhm.
will need the capability for the root of my file system.
No,
And
no.
So now I'm
No, it just, what happens behind the curtain is that the web browser allocates an anonymous memory object. So it goes to core and says, I want an anonymous memory object, a data space, we call it. And this is just a container for memory. Then it loads the web application or the plugin into this container.
Not a plugin. I mean, I'm just downloading.
You're downloading the file.
Downloading something.
Okay.
So it needs to store it in the file service.
Yes.
So that means it needs the capability. I mean, if you have a POSIX model,
Yeah.
you
We don't.
need.
We don't. That's the fundamental difference.
But you said you had a POSIX.
No, yeah, but that's just not a first level citizen. It's just like the Linux that we can have as an execution environment. We could have a lightweight
No, I understand.
environment.
If I run Linux in a virtual machine,
Yeah.
that I get all the badness of Linux.
Exactly, and for
But
this
if
reason,
If I use the POSIX, your POSIX compatibility layer,
yeah,
if you present my POSIX compatible program with a complete POSIX model,
yeah,
then I get all the ptrace badness and the
Exactly.
global file system
Exactly.
and the everything.
but there's a but. For example, you can tweak this POSIX environment for each use case. For example, as a developer, you have typically an editor running, editing your source code. Yeah, and so the editor needs the capability to access the source code in a read and write fashion, but not any other file. So you can have a separate virtual POSIX environment just presenting this part of the file system. So there's no global file system. It's only the local stuff that this scenario is needing. In the second stage, you want to compile this thing. So the compilers must read source code from the source code directory and write to the build directory, and you can express this in the configuration of this execution environment. So for the compiling stage, you just use another POSIX emulation environment with different rules, but with another virtual file system. That's not a global. There is no global file system containing all the files, but each part of the system has a local view. And in the third stage, you want to run the result of the build. You will probably only provide binary to be executed, but not any source code and not any other things. So that's really the idea, to have a kind of POSIX emulation environment to run those programs, but not to emulate the semantics of the whole of a real POSIX file layer. So that's the idea.
Speaking from experience, what we found with Amoeba, with the moment you have a POSIX layer, you want to run Emacs in it, or nowadays Eclipse. That depends on so many other libraries, which all have their dependencies. That what you are essentially creating, that the environment you're creating for that program is essentially, the whole wide open POSIX environment.
But that's the actual trusted computing base of this program. We cannot change that. If you want to use this legacy program, you have to carry along all this trusted computing base. There's no way around it, except for modifying the program. But we want to, for example, use existing new software like compilers and and we accept these large dependencies for our normal Linux system, and we are also willing to accept that the same amount of complexity on our system as well, but we need this functionality. So, but that's not yet done. So what exists right now is a C library that has no real files. You cannot really open a file. It implements just a normal POSIX-like functions like the string functions, memory allocation, and stuff like that. Math library, all the stuff that is needed by those typical libraries like the PNG, FreeType, and the Qt framework. So we can really easily use this C library to port a lot of different libraries. And as soon as file access comes into play, we can, and enhance the C library with a plug-in based facility. So we can plug in a file open handler or that gets consulted as soon as the program opens a file, and this file handler can then manage the file descriptor for this particular file. So we can, for each application, we can right now pretend certain files. I give you an example. I ported the Gallium 3D libraries, so Mesa, that's the 3D API used on Linux. And what happens there is that the program uses the device def DRM to communicate with the kernel, like passing graphic cards commands to the kernel. So the driver just makes open def DRM and then mmap a file or something like that. And of course we don't have such a def DRM because we don't have a file system. So we put in a plugin into the C library which just got to know, here's an open access. Are we willing to handle it? It's def DRM, okay, we take it. So the plugin takes over the control over the file descriptor, and for the mmap call, the plugin is consulted, and the plugin can seamlessly map to the memory and get it, but organize it from somewhere else. So we can use those software without modification by just changing the environment a bit, so that the software feels right at home. So, yeah, thank you.
Well, what happens if you have a number of applications running? They're all using legacy applications maybe, and they're using a fair amount of memory. And you have an application that needs to handle large documents, a graphics application or something. And that application, that memory is not available anymore. But it is available in the other applications that have it reserved.
Yeah.
Is there any way through the system to, in an emergency situation like that, to get the memory that is in the hardware of the machine, to collect it back to run that one program with that one large document?
So basically, to answer the question, the quota that is assigned to each process in a subsystem is completely known to the parent of the subsystem. So if the parent decides to adjust the quota, it can transfer quota from one process to the other. So you can imagine a parent that just allocates quota to processes as soon as the process performs a memory allocation. So an on-demand quota increase. So this would basically circumvent the whole trading idea for a subsystem. Another more clever idea, I think, is to have to use Slack memory in a more semantic useful way. So right now, if we have Slack memory, so unused memory in a Linux system, the Linux kernel uses the Slack memory as a block cache and for nothing else. But on Genode, core knows about the Slack memory because it knows what quota is available, and it knows which allocations had already been made, and it has an overview about the Slack memory. So it could provide a special service, let's call it cache, which allows the client of the service to allocate any amount of memory, but only make a certain window of this memory visible as the shared memory arranged. And a client of this process would first donate, for example, 2 megabytes of memory to core. So core would establish this window and would pin some content in there. And this application can then allocate some other memory, and this allocation could be going fine because there's enough Slack memory. Then another memory object would be created, and the user could make it visible through the window and use it. But if the allocation fails, then it will just remove the previous content of the window and add a new information and drop the old information. And now if there's pressure in the system, so if the Slack memory gets smaller, then the core can decide to remove all those non-visible cache memory. And this way, typical caches, for example, image caches for web browsers or the image caches for viewing application, could be allocated exclusively using this service with the knowledge. The program has the knowledge that this memory is not really guaranteed to persist. It can be discarded at any time.
Sounds good. Is it implemented yet?
It's not implemented yet, but it fits very naturally into the current architecture. So this would be an idea to approach this problem.
That's an important question I had about the architecture. I have one important question remaining in my mind about the license. I understand that your business model is dual licensing GPL, but as far as I can see, if you want to write any program on Genode, you have to link to your libraries to communicate with your system services. And those libraries are GPL, so you can only run GPL compatible programs on the current system.
That's right. So all PST programs or open source software.
So any commercial programs or open source that is not GPL compatible can't run on the open version.
Actually not, and that's by intention. So we already thought about it, but as soon as we would add some kind of a loophole in this construction, people would find people would find ways to exploit, and so to like look at a Linux kernel with the binary modules that we load into, and I think we are not on a really solid ground regarding to this licensing speech and the whole law that is involved over there, and this would certainly open some kind of a gray zone, and I don't think that we will do it.
But right now it means that Genode is not a real platform. It's only a platform for GPL compatible software, not even all open source. It must be GPL compatible.
Yes.
Except if you pay for the commercial license. So it's a great architecture, it's a great design, and I've always thought the world needs it, but it isn't a real platform at this moment. And it's just a licensing question. Do you have a plan to change this over time?
Currently, we don't have a plan. So this is not just for the moment, but so the idea is that so we once had the idea that we would expose this POSIX emulation environment, or creating a special exception to allow users to just use this predefined API and allow applications using this POSIX API, because it's obvious that an existing POSIX application is not derivated work from Genode, so which is the intention of the GPL. It wants to free derivated work from the set derivated work free.
But it also uses the criteria of running in the same address space. And to communicate with your servers, you need to link with your libraries.
Yeah, that's true.
To abstract the interface, I suppose.
Yeah.
So you're running in the same process. So according to the GPL.
So this would allow us to implement a special exception into the GPL, and doing such an exception is a very risky undertaking, because if we have a slight misspelling over there, we have just created a loophole. For example, someone releasing a GPL library that just tunnels our Genode interface through a file interface exposed by the POSIX API. And that's just not what we really want. So it's a really hard topic.
Yeah.
And if we release it more freely, so if we then we cannot apply our dual licensing model anymore. Yeah. So that's also.
I totally understand the business side, but it is my holding back from seeing it as a full platform for the whole world.
Mm.
So basically, your plan is to be bought up by Nokia or something.
No, we don't have any plan.
GPL it and then,
so, given our background, we started this company because we wanted to drive this technology forward. So when we finished the PhD at the university, we thought, okay, we can stay at the university, but this will not lead our project to the real application. So we could also apply for a large company to be an employee, but then we could not develop further this technology at all, because we would have to do the job assigned to us by the company. Or we had the possibility to apply for a job at a smaller company where we can have a bit more influence. But in practice, we would also not be able to work on this technology anymore. And so the only way to bring this technology forward was founding this company. And this is the background that we have. So
the very same issues with Silver, yeah.
Maybe one last question about hardware security. This is all very much related to software security and virtualization. Have you also looked at hardware security, like things like Blue Pill?
Blue Pill. This is the VT-based exploit. Is it right? so basically, to protect the software from such exploits, kind of authenticated booting mechanisms must be used. And so this is like in the form of TPMs chips implemented in the current PCs. And using such TPM chips, each application can get some kind of a passport of the complete software stack executing this application. And with the Genode architecture, there is a very natural way of how this can be used, because each parent can provide the authentication information for the child. So there's already a stack of software which is very well defined, and so authenticated booting protocols could be implemented very naturally in Genode. And then you have to, of course, to secure the root of trust, which is typically the bootloader, which is always needed, and then you are fine. So then there cannot Blue Pill be intercepting your system. But basically, the whole idea of Genode is that it's possible to transparently enter new components in between in a tree. So basically, this is Blue Pill in Blue Pill in Blue Pill. So that's the idea of the architecture. So yeah. And maybe on such a system, it makes much more sense to have authenticated booting, because the root of the tree is much smaller. It needs to be evaluated only once, and then it can be reused. If you evaluate a Linux kernel and have a signed Linux kernel and declare this as a trusted Linux kernel, there's a very little chance that this will be used in 5 years or useful in 5 years. So it's constantly changing, and bugs are discovered, and you would have to re-evaluate Linux. And with this concept, only the little bottom of the tree needs to be looked at carefully.